Okay, so the plan is to go through the first 2 pages today and the next 2 pages on Thursday. The problem set kind of divides up nicely here. So the first 2 pages, they cover firstly the idea of linearization and a little bit involving differentials. And then the last 2 problems are just sort of a little funny, but it's just basically name the appropriate theorem. I guess that he split the slide or the notes into 2 different sets of slides. So yeah, we'll be doing the information that pertains to 10-8, which is linear approximation of differentials. And then next time we'll do the stuff involving local min, local max, and absolute max on a closed interval. All right. So first, let's talk about what this idea of linearization is. So the idea is that you're given maybe a function that isn't linear, some kind of curvy looking function. But then when you zoom in really close to that function, it ends up flattening out. And that's just because that's how usual well-behaved functions work. You could probably come up with really bad ones, but the functions that you tend to encounter are ones where they have this nice property where you zoom in real close to them, how fast they change ends up being approximatable by a line. And so that's why linearization is a thing. That's why it works. So what you need to know for it, so usually we have this formula for linearization where it's f of a plus f prime of a times the quantity x minus a. Oh, I keep doing that. I need to scroll a bit more to the right. Why does this not work? Okay. Times x minus a. And so the idea is that for whatever the function is, it is trying to center a line about a that approximates the behavior of the function near a. So this kind of x minus a right here, that tells you you're centering it at a, or yeah, at x equals a. And then this slope is just to make the slope of the line match up with the way that the function is changing at a. And then this plus a just makes it match the height. That's how you should think about this formula of linearization. And if we're kind of being more accurate or precise about it, you should realize that there's sort of a dependence on this value a itself, right? For whatever particular a you want to center at, you will get a different linearization. So the better notation would probably be something like this, but we never end up specifying what a is usually. When we linearize, we just say L of x is equal to something. So this is the overall idea. And with that, we can basically just go through, I think, the first 2 problems. Yeah. Any questions so far? No. Okay. So, all right, here for number 1, we're told we have a function s of t, and we don't know how to write a nice formula for s of t, but we do have some data about it. And with this data, we can linearize. So that's going to tell me we should have a specific position and a specific velocity. Yeah. So we have s of 1 and s prime of 1. So translating what is written here is telling me s of 1 is equal to 5 centimeters and s prime of 1 is equal to 2 centimeters per second. So these are the 2 pieces of data that I need to actually plug into this kind of formula. And so we would construct the linearization, which is just some other function. And then we're going to plug in at t is equal to 1.1. Okay, so linearization is going to say, in this case, it might make more sense to call this t instead of x, since this is a time. So we may as well do that. L of t, and then s of 1 is what we would normally write. So I'm just going to directly plug those things in. 5 plus 2 times t minus 1, right? If we just follow what the formula for the linearization, what that is, it'll give me this as the formula. And I would not bother, I would actually not expand this out or anything. The fact that we have it written in this format that is centered will help us to do the evaluation. So you shouldn't do any manipulation of this afterwards. Instead, you should just plug in. So we want to figure out the location at t is equal to 1.1. If I plug in to this L, I'll get the answer. 5 plus 2, and then 1.1 minus 1 is going to be 0.1. So I'm going to get 5.2, and my units are centimeters. Okay. And so the key thing that I haven't written here, the thing that makes this work, is that linearization is supposed to approximate. So if we were to write this last part, it's saying that S of 1.1 is going to be approximated by the linearization function. And this should be something that's said in the slides. I didn't thoroughly go through the slides, but the idea is that for small deviations in your input, linearization should be okay, and it should approximate just fine. You can imagine, though, that if your t, or if your separation from 1, if that was like 3 or something, or 2, even if it was just 1, like if you're trying to calculate t is equal to 2, then linearization may not be very good. So because you really expect that your change from the center to be a small quantity. That way linearization does make sense. It's all because the idea is that the linear approximation is good if you're zoomed in really, really close to the function. That's the overall concept here. Okay. For number 2, it behaves very similarly. It actually gives us the information in mathematical form. So we can just straight up write the linearization for this. So the function that we would want to plug into is r of p, but we don't have the actual function r, but we have some data about it. So the linearization that we can get, maybe I can use p for this. That's fine. So it would be r of the specific p-value, which is this 5 million. Okay. Plus, and then the derivative, so that'll be 40,000, and then it's going to be the thing that centers it correctly. So this is going to be p minus 500, because the two pieces of information that we have are when p is equal to 500. Okay. And so this is what we have for the linearization. And now we just need to use it to evaluate at 502. So all we do is we plug in 502. And I'm just copying a bunch of zeros. Okay, so this is going to be 2 times, so I'll get 80,000. Okay, sure. So that's 5080 000. And this is in dollars. That's the estimated total revenue, right? And yeah, maybe it's a better thing to somewhere say that this L of 502 is approximating the revenue at 502. The whole point behind why we're doing linearization in the first place. Okay. 3 is now pretty different. So 3 uses the idea of a differential. So in the past, we've been dealing with quantities like dy, dx, and we probably have told you, like, this is not a fraction, you shouldn't split the things apart. But now we're sort of going back on that statement here. But it's still true that you shouldn't think of it. It's not completely a fraction, but in some instances you can treat it like a fraction. Okay, that's kind of what we're trying to say. And here, though, this dy, the way you're supposed to think of it, I guess, is that it's kind of saying, like, this is how much a change in y, how it will relate at the end to like a change in x. So it's almost as though you could take the derivative of this equation with respect to x and then just say, let's multiply both sides by dx to bring it to the other side. You'll see, because when we just say to take the differential, we just take the derivative here, we'll get cosine of x, and then you can kind of think of this as implicit derivative. Like the derivative we're taking with respect to is sort of like a dt almost, and we end up with a dx. So it's hard to explain, but this is the correct answer. And so you can kind of see like, oh, you could have thought of this as doing a dy dx and then just switching the x over. When you read this thing though, it's not the same exact thing as saying dy dx is equal to cosine of x. This is like a statement about a function, but this is a statement more about like how rates change. So this is saying that like for a specific x and a specific change in x, if I know that if my change in x is dx is like going from 1 to 1.01, my dx would be 0.01. How will the y change? Y being the original guy here. What would be the discrepancy between these 2 points that we're measuring against? And so this is saying like, oh, the dy, the change in y should be about so much. This is kind of a way of like approximating error in a linear sense. So there's because you can always compare it against the actual, which is what we will do very soon with like error. So these things that involve differentials kind of assume that our rate of change is linear. That's why we do calculus, why we are doing linear approximation in this section. We're kind of assuming that the way that a thing will change from time t equals, a to b, we assume that the change is going to be kind of linear based on just the derivative at a specific point. And so then that is an approximation after all. And we can test that against actually plugging values in, which is what we'll do in 4. But for here, I'm kind of going all over the place. But yeah, hopefully this part makes sense. You're just taking a derivative and you get this kind of expression. Then we use it to estimate sine of 0.2. Okay, so right, what I'm getting at is if we so the nice value that we would be thinking about is sine of 0. 0 is an easy number to work with. So the way that this kind of sets up is that we have x is equal to 0, but our dx is equal to 0.2. Okay. And so with that, we can plug into this expression. That'll tell me that my dy is going to be cosine of 0. Maybe I'll write that out explicitly. Cosine of 0 times 0.2. Cosine of 0 is going to be 1, 0.2, so I get 0.2. Okay, so that is the discrepancy in y. That's what I expect to happen when I go from sine of 0 to sine of 0.2. So I have to tack this dy onto whatever y would be in the original data point, I guess. So the way that you would write this, I guess, y equals sine of 0.2. Well, that's approximated by sine of 0 plus the dy. Okay, well, sine of 0, is just 0. And the dy is what we calculated just before. So we get that this sine of 0.2 should be approximately 0.2. And then you can check with the calculator to see how close you are to that. This is just an approximation based on calculus, right? Okay, so but this is how you would answer part B.
Would there be any labels for that one?
Labels. Oh, you mean like units?
Yeah.
There are no units here, so no units. Yeah, that's a good question. Yeah, I should probably also box this guy. So yeah, this one had dollars, the previous one had centimeters. But here, yeah, this is more abstract, no units. All right. Number 4. Okay, so now this number 4 is a much more typical problem. Feels very much like the type of problem you normally see on the test. Okay, so find linearization, you're just given a function, and you're also told where to center it at. And you can kind of look ahead and see, like, why are we centering at 16? Oh, because we're trying to calculate 15.2. We're trying to calculate the square root of 15.2. So you can see, like, this is how we're going to use the linearization afterwards. Okay, but like to do the linearization, just remember, and then for this, I would actually just write the formula. F of 16 plus f prime of 16, x minus 16, right? Remember, like before I used a for these, but a in this case is the 16. A is the value you're centering your linearization at. Okay, so now what we have to do is figure out these two values. Well, square root of 16 is just 4, but the square root involves a little bit of side calculation. So the derivative is 1 over 2 root 2, or no, root x, 2 root x, yeah. And then f prime at 16 is then going to be 1 over 2 times 4, so 1 over 8. And so this equation is the linearization for this function at this value. And now we just use that to approximate this. So to spell everything out, I would say this square root is approximated by linearization, by using the linearization formula that we just found at 15.2, and then I would plug it to it. So this is going to be, let's see. So this is one of the mistakes that I do see is when people subtract, but then they don't put the negative. They forget that like it's actually supposed to be a negative quantity. So this is going to be a negative 0.8. And so you get a negative 0.1 here. So you get, maybe I'll just write it, 4 minus 0.1, which is equal to 3.9. That's what the linear approximation gives as our answer. And then the idea is to check with a calculator. So I do have a calculator. Maybe I can put it off to the side and I'll just, yeah, sure, why not? I'll show you guys the calculation just to be extra convincing, I suppose. New share, full screen. Oops, oh no, I don't want that. Okay. Right, so you need to know what the expressions are for error, relative error, and percent error, and I believe they show up on the slides. So error is the actual minus the expected absolute value of. Relative error is going to have a division there. Maybe I'll just write the formulas out first. Is going to be the, instead of expected, I would say like the approximation. Yeah, approximation. Let's use approximation. That sounds a bit better to me. Approximation, actual minus approximation divided by the actual, also in absolute values. And then the percent error is just the relative error times, and then you switch it over to involve percents. Times 1,000 computers lagging. Oh, that's because it's times 100%. Okay, so those are the three formulas. And so when we calculate this, let's see. So the square root of 15.2 is actually this value. And then we would just subtract it off from 3.9. And so the actual error we get when you absolute value that, it's, I guess I would put it to that many decimal places, just so I can actually see what the number is. Then when we do relative error, well, it's going to be, oops, no. square root of 15.2 minus approximate, which is our approximation is 3.9. And we all divide that by square root of 15.2. So we get, come on. Something's being weird. Okay, 0.00032. I don't like rounding. 889. Yeah, and then yeah, just percent error. You simply turn this value into a percent. So multiply by 100 and then tack a percent sign at the end. Well, that's just going to bring the decimal point there, 0.032889%. So these are really small values to be working with. So I guess that means that your approximation is pretty close, right? So for this function, it works rather nicely. And that's why we do linear approximation. And there's actually different forms of approximation out as well. So maybe I should just tease this fact. Like if you go on to Calc 2, you start learning about other kinds of approximation using like a Taylor series expansion. So this is just like the Taylor series expansion for n equals 1. Like you only use one term of your Taylor series approximation. And there's also Fourier approximation, which is probably more like what engineers use. But okay, yeah, so this is a good start for all that theory. Let's keep going with the problems. Number 5, we use differentials to estimate the volume of paint needed for coating a sphere. Okay, so first of all, notice the change in units, right? 1 meter versus 1 millimeter. So if you don't notice that, that's going to be a big problem. And so I'll say this is actually 0.001 meters. And so the idea is that we have a sphere. Maybe I can just draw the sphere. I just draw it like as a little circle. And then when we put some paint on top, it's going to just introduce like an extra layer. It's going to increase our radius by this 0.001. And so that's 0.001 is our dr. If we are thinking of volume of the sphere, let's see, 4/3 pi r cubed. That's the formula for volume of the sphere. We go from r to r plus this dr. Volume is going to go from v to v plus some dv. So that's why we need to calculate what this dv is and then tack that onto the original v in order to calculate what the, well, actually, no, we don't need to tack it on because here we're just trying to estimate the volume of paint. The volume of paint used is just going to be that dv. All that extra volume that all the extra volume is going to come from the paint. Okay, so let's do the differential. Let's take the differential of this equation. I think that's how you say it. And so you get 4 pi r squared dr. Okay. So like in my head, it's almost as though I'm taking a derivative with respect to time and I'm just like getting rid of that dt at the end. So it's sort of like an implicit derivative, sort of. Okay. All right, then we need to plug in, right? So r we're given because that's this 1 meters here. And then this 0.001 is my dr. So I can just plug in. Yeah. So we get, well, this is just 1 that disappears. So we get 0.004 pi. And the units in this are meters cubed because this is measuring a volume now. And I can actually do a little, I did calculate this in the past. Oh, it's actually up here, isn't it? Yeah, it's this expression right here. So yeah, 0.012566 meters cubed if you prefer decimals, which sometimes I'll agree that it makes more sense to things in terms of decimals. And then just like as a sanity check, what I did here in these lines is I actually calculated what the actual difference would be, just to make sure that like the approximation given by calculus should match up with if we just do the naive thing of just plugging in. So just plugging in, you see that like this, I'm having r equals 1.001 minus. I'm just taking the difference of the two spheres, and you get a very similar value. It's very close. So good. like little sanity check. All right. Any questions so far? Okay, no. And we could probably do page 3 as well. I don't just trying to think, should we do page 3 or not? Well, let's go through 6 and 7. So at least for this, I want to find whether or not the theorems are mentioned anywhere. Because I thought that the theorems were probably mentioned in like a previous section, and maybe just we forgot about them until now. Or am I wrong? Raleigh's theorem and mean value theorem show up. Okay. Right. Well, so one of these is intermediate value theorem, and one of these is mean value theorem. And I guess it's just you have to like figure out which is which. I don't know. Like those are the only two theorems that you really encounter, I think, in a Calc 1 class. So like reading this, right? This is saying you start at 70 miles per hour, you go to 80 miles per hour, and the conclusion is that at some point you must have been driving 75 miles per hour. So that you should really think of this as being the intermediate value theorem. Right, which we typically abbreviate as IVT. And so like the thing that makes that kind of clear to me is that well, you're starting at 70, you're going up to 80, and it's the idea like you got a continuous function. So in this problem, velocity is your continuous function. When it says something about acceleration, that's the derivative of the velocity function. So the fact that the y-axis is the velocity, so acceleration. And they're using acceleration like the English kind of sense, not really the mathematical sense. So yeah, 70 to 80, at some point your velocity must have been 75, just because velocity is a continuous function. You can't just jump from some velocity to another without sort of going through everything in between. So, and 75 is an intermediate value, right? Hence the name. Okay. For 7, this it seems like is something that you cover in lecture 14. So on the videos, yeah, I guess you cover that a bit later. So this it's relating an average velocity with an instantaneous velocity, and it's saying that if in some trip you had an average velocity, this is saying that at some point you must have been going precisely at that average velocity. And if you stare at mean value theorem, you realize that that is what mean value theorem is saying. So since I think this is something you encounter pretty much now, I'm gonna just copy this over and stare at it with you guys. Yeah, so this is what mean value theorem says according to the slides. And so we have some, just like with intermediate value theorem, we have some preconditions on our function just to make certain that we can say this final conclusion, okay? Like the function's got to be nice. It's got to be continuous. It's got to be differentiable. These are just nice properties of the function so that we can actually conclude things. All right, then it's saying, okay, so A to B are starting and ending times. And this expression on the right-hand side, this is just average velocity. This is what you would calculate as being the average. In a pictorial, does he doesn't have a good picture of this. All right, I'll draw a picture of this. All right, draw your typical picture, right? Your typical picture from A to B. From A to B, the average velocity is given by the slope of that line that I just drew, this line in blue. And the idea is that at some place, visually, what you do is you just slide that line up and down until it intersects precisely at one point. So I'm just gonna slide this down to like around here. So you can see like it kind of, I'm trying to make this line parallel and I'm trying to make it intersect at one point. And so that one point, that is the special little C value where the derivative at that point matches precisely with the average velocity, the average change from the two endpoints of the trip. So mean value theorem is just guaranteeing for some average, you can actually find a place where the derivative obtains that average. This instantaneous rate of change is equal to the average rate of change. This is the picture that corresponds to this equation. And this statement is exactly saying that. The average velocity was 75 from point A to point B, just gather the data. Well, then there was some specific point in time where you were traveling exactly at that velocity. Right, so this is mean value theorem. And like probably people could say this is MVT, but I don't really think I see that. So I'm not going to write that. Okay. So we have 20 more minutes. Should I keep going? I'm going to keep going. Or... Yes, I see one yes. Just want to do it. Oh, okay. Yeah. Yeah. Maybe at least today. I don't know. I could at least do 8. It has 5. G is like 7 parts. 7 parts. It's quite a lot. All right. So there's like a maybe I'll full screen this back, and then I'll switch this back to full screen. We don't need to calculate anymore. Okay, so now we're talking about this these words of like local min, local max, and absolute min and absolute max. Like they show up all throughout this problem. So you have to understand what these things mean. And if you stare at the definition in the slides, oh no, my computer's being weird again. Yeah, the information in the slides is kind of, I have to translate what it means, I guess. But really, what it means, like, if something is a local anything, that means you look at the values close to it and you see like, oh, it has that property with respect to like the things around it. So to be a local min means that it's smaller than all the values around it. To be a local max means it's greater than all the values around it. So this is a particularly weird point right here that I'm pointing out with my cursor. This is a local max, right? Because the values that are close to it, well, on the one side, you're going to jump down here. On the other side, you're going to jump way down here. And so this guy's a local max. And so you can kind of do that for everything. And that's how I would start this problem. With absolute max, the absoluteness means that it's the biggest with respect to like all possible inputs. And so that's why like whenever you see an absolute statement like absolute max or min, it will tell you on what interval. That interval is very important. Otherwise, you have to assume it's the interval is the whole real number line, which that is a very strong statement. But let's go ahead and let's label some points. So there's this point here, there's this point, there's this point, and there's this point. Okay, so I would start just by labeling the picture and then translating it because it turns out there's actually 3 absolute maxes. So this or local maxes, sorry. Yeah, so this is a max, as I was previously saying. It's greater than all of its neighboring points. This is also a max, and this is easier to see, right? This is your typical picture of a local max is one that's like close to its neighboring guys. This guy is a min, right? It doesn't matter the fact that it's it doesn't have a derivative there. What matters is like, oh, it's lower than the values around it, right? It doesn't matter that the slopes all of a sudden just jumped. And this guy is, it's more like this one that's just floating around. This one is a max because you can plug points that are around it and you're still going to be higher. Okay, and so from that, we, for local min, we only have this 1 point there. So that's going to be 2, -3. And the other 3, we can just list them out. So -2, 4, 0, 1, and also 4, -1. Okay. Right. Now for C, does this function have an absolute minimum on -infinity to infinity? So we look through and we see like, is there some minimum value that the function takes? In this problem, there is. Right? It's It's actually this value. Notice that like you could also be misled and think that, but in fact, the function doesn't take that value. The function takes this value up here. So this is not a min, this is a min. You have to attain that value. You can't have an open circle. Okay, so the particular point, I'll say yes first, and then I'll say it's the point 2, comma, -3. Okay, now D, that's an important distinction. Now D, does it have an absolute max? Well, this thing shooting off to plus infinity tells us it doesn't have an absolute max. Okay, so the answer for D is no. Does that make sense? Hopefully that makes sense. Okay, no dissent. So okay, everyone agrees. I'll assume. All right, E. E and F actually. Yeah, let's look at E and F. So now for both of these, it's specifying our window that we're looking at to be -1 to 1. So it's like we take this function and we just pretend that we ignore everything outside from -1 to 1. All we care about is this small interval here, -1 to 1. And we're trying to figure out what are the absolute max and absolute min values that the function takes just inside of this window. Okay, well, the absolute max is definitely going to be this point up here, 0, 1. The absolute mins, notice, so this is kind of a technical thing, but see how the window it includes the endpoints. It includes the -1, includes the 1. That means we can plug in at those points, and that's why we can say that it has absolute min at -1 and at 1. Both of them have take the value 0. Okay, so that's what we're going to write down. Absolute max is, where did my cursor go? Absolute max is 0, 1. Absolute min -1, 0, and also 1, 0. Okay, and now G shows us an important distinction. So what happens if we now change our window just slightly? So if we extend it over to -1, 2, we're just bringing this window and we're stretching it over to here. Well, now we've introduced lower values that the function will get. So that turns this -1 is no longer an absolute minimum. Instead, we end up with this value as being our minimum. So that gives us the, 2, -3 is now the absolute minimum. And so this is showing you that window is very important. That the window will dictate for you what those min and max values are going to be. This is going to be very important with, I guess, the process that we use to do these kinds of calculations. So, because normally we're given a function, not a graph, and we will determine data about our function. In fact, number 9 is exactly that. Yeah, so I'm against doing the whole problem set in one day, but 10 minutes, I can definitely finish this one problem, and then we'll just leave the last problem. That means that like the next recitation is going to be like maybe 15 minutes long, but well, I guess we'll live with that. Okay, yeah. So let's see how this process works with like just a function instead of a graph. Okay, so this is kind of this is a very standard type of problem, finding the absolute max and min value that a function has on a specified closed interval. So in the slides, Craig calls this the closed interval method. And so you can look at examples of that. Okay, the closed interval is very important for the absoluteness of it. You can always, so in calculus, you can always find the local min and maxes. That's just given by taking the derivative and setting equal to 0. Those are called critical points. I don't know why we haven't used that word yet, but those are called critical points, and those will be where like you expect a local min or max. But then to say this is actually a global and absolute min or max, you need a closed interval to talk about that, and you need to plug values in and get values out. Whereas with local min or max, you can just look at like how the derivative, like if it's plus to minus or minus to plus, you can say like, oh, this is a local min or it's a local max. You don't need to plug values in for that, but absolutes you do. Okay, so let's go ahead and do this type of problem. G prime, we start by taking the derivative and setting equal to 0. So G prime of theta cosine of theta -1. Okay, and the usual process is we set this equal to 0 and we solve. Okay, so that's going to give me that cosine of theta is equal to 1. And then I have to think about the unit circle. Think, when does cosine take this value 1? Well, it only happens at this particular point on the entire circle, and that corresponds to theta equals 0. Normally you would say like, oh, there's like plus 2 pi, minus 2 pi, all these extra 2 pi's. This window forces us to only consider one value. Okay, so that window is important. That gives me theta equals 0. Okay, so what does this actually conclude for us? Ordinarily, we would say this is a critical point. And so then you would draw a number line, think, is it a min or max? But we can shortcut that. We can skip that step, because absolute min or max, if that's what we're looking for, all we need to do now is plug in at all critical points, which the only critical point we found was 0 here, and at the endpoints, okay, which are this minus pi over 2 and pi over 2. So we just plug in, and I may as well just write these in order. I know I need to plug into all three. And I'm plugging into the original function because I want to figure out what is the value that the function takes. What is the height of that function? Okay, so well, now it's just thinking like, okay, what is sine of pi over 2 minus pi over 2 to I think this is a minus 1. Yes, minus 1, and then plus pi over 2 for this. This one would be 0, and this one would be 1 minus pi over 2. Okay, well, so I can think about this without using a calculator. Maybe that's the point. So this pi over 2 is 1.5 approximately. So this is greater than 0, and this guy got less than 0. So we end up not seeing this critical point in this problem. This guy ends up being an absolute max, and this ends up being the absolute min. And if you wanted to, you could write this in coordinate form. So it seems like on his slides he's doing that, so I may as well do that here. So the absolute max is the coordinate, is located at the coordinate minus pi over 2, comma, and then, well, I can't do anything to that value, so I have to just write it out. And then the absolute min, same thing, pi over 2, comma, 1 minus pi over 2. There we go. And yeah, so that's how you do this type of problem. And we'll do, next time, we'll do 2 more problems that are very similar. Okay, but I'll encourage you to try doing it on your own first, and then we'll go through it next time. All right. So that's it for today.